let's get going. Welcome. Glad you're here. Statistics 451, so applied statistical methods. And so we'll be meeting here Monday, Wednesday, Friday to go over topics and computing and general ideas. A lot of course material will be delivered. I'll make handouts for a few things, but a lot of it will be put in Canvas, like I'm sure you're used to. Announcements and then assignments will be posted eventually, and along with solutions eventually, or at least comments on solutions. A number of the projects in this, or assignments in this course are small data analyses or applications of models to that, so there's a number of different ways to phrase solutions, to investigate things and present it or write it up. So sometimes the solutions will be essentially comments on major themes or key points, rather than a complete entire write-up of every detail that might be there. Files get uploaded on Canvas, so under lecture notes, for instance, there's a little directory structure. But so the first one, there's the things that we have, the class schedule, and the student's questionnaire and syllabus, and a few things that we might look at examples of models today, kind of by way of introduction. And the syllabus information is in there. The course will be recorded by Tegrity. This class is enabled for that, and so if you happen to miss, for whatever reason, job interviews, other activities, family, sports, just get sick for a day and you just need to stay out, it should be recorded, so easy to stay up with information. Right? And in general, if you have things going on and need to be away for a good reason, let me know. This is a smaller group. A lot of the projects are not just give me this number, but look at a plot and then interpret it. So I'm willing to grant extensions, but do try to let me know in advance if possible about your things, and it can be flexible to help you to do what you need to do besides just this class. So in terms of syllabus, let's see where all those things go. Trying to figure out what's in these things. There it is, right? Right, so we'll meet here. The office hours I've put up here are, after this class, and then there's kind of a lunch break, and then before my next class. That's most convenient for me Monday and Friday, and then a couple other time Tuesday for that. For the first half of the semester, most of the assignments are due on Wednesdays. Wednesdays. Right, so that's why it's focused on Monday, Tuesday to answer questions during that time, and Friday if you start looking at it before the weekend. About halfway through, we have a one-day break or a couple-day break in the semester, and that kind of throws things off. So about halfway through, I'll assignment on Friday, and I'll move that Tuesday office hour to Thursday. Right, but I'll just remind you when that happens. My other class is, hi there. Here you go. Thank you. Yeah. My other class is Monday, Wednesday, Friday at 1:30, so I won't be around at that time. But if these other times don't work, if you have other classes, labs, or something else, or just want to schedule a little time out of it to talk about other things, majors, minors, in statistics, data science, or mathematics, or intern possibilities, or other things that are done in professional career, and of course topics, or other research topics. If you have a data set for another class, some of you might be preparing senior projects or thinking about them, and you want to talk about that, and we need a little bit more time, I'll check my schedule, and we can try to arrange some other time that works for you. I didn't schedule anything before this class, but I'm often in earlier before this class, so that works too. Right? So this book that we're using is designed as kind of a continuation of study of statistical methods, how different data structures get analyzed to answer certain different types of questions. It de-emphasizes some of the formulas for some of the interpretation and issues of checking models, interpreting, presenting. Will kind of augment some of the things in there with a little bit of notation, so that it kind of gets both the kind of more, you could say rigorous, but in terms of just notational, compact ways of writing things down, as you might see, but a lot of it is applied. How do you use it with data sets, which I think makes it kind of interesting and useful as a bridge. If you would go on to study in graduate school in anything that would use statistical methods, it will be heavier on writing down equations, solving equations. We'll do some of that, but so this is kind of a bridge between doing things a little more elementary, more complex models, and a more sophisticated thinking about how they get used and evaluated and what their purpose is, in a way. Right? We plan to use the R statistical package. You don't have to have any background for it. Many of you have used it in one course or another. It is my philosophy of that is you learn how to use that by using it. It's like a language, and we'll start out building up. A lot of the things can be unified across different methods in our class. So we'll spend a day talking about installing R and RStudio, which is a nice interface, getting data into R, and we'll take that up a number of times throughout the course as we get new data sets from the internet or from Excel files or from other things. How do you get them in to R and output graphs, and so on. We'll do that. It's good to have some back a 200 level class as the prerequisite. Right, and then so there's a few other things in here about learning objectives, the idea of replication, explaining the rationale for using a few statistical procedures, and then implementing them in a number of applications, and then comparing the data to the model, doing some diagnostics, or reassuring yourself that the model you're using seems appropriate for the data. Right? So the grades in the class, there's homework assignments. These in a 400 level class, some classes would choose to have just a few large assignments. This one has more, but it'll be kind of smaller, so on a particular chapter or two, a couple of the projects, and so it kind of is work to go along with things as we're doing. You can talk to other students and to me about the assignments, but everybody should write up their own. It'd be important to be able to do the computing on your own, to understand what the commands are doing, because towards the end of the course, I'll probably give a few less details about, we'll get a new data set and I'll say, describe the data set and do some preliminary checks. Well, that'll be the commands that you use with the beginning part, so if you're familiar with those, it can be modified. And then in the final project, you might want to try more things. Right? The homework is one part of the grade. There would be a couple projects in this. The first one is a little bit shorter, considering some linear models and regression to be through kind of the first part of the book. The chapters in this book are, not overly long. They could be taken in a week or a couple per week. A couple of them are smaller or very related topics, so they kind of cluster. Right? And so that will primarily have a paper to write up. I haven't quite decided about the length, but those papers, doesn't have to be terribly long, whether it's 5 to 10 pages. Some of that could include output and some, graphs and things like that. The second one would be done at the end and probably would include a more complex model, more involved data structure. That report would be a little bit longer, and then will be a final presentation based on that one. And so instead of, in lieu of having an actual written final or exams, there's these a project and then a project and presentation. Right? And so, and of course, at this level, I think that's really useful to think about writing about what you're doing, investigating things a little bit more. There is a role at some level of memorizing formulas and doing things if you're going to do this as a career and go into it in great detail. But I think that the presentation and communication is where it would be interesting to see, and you get to tailor it to your interest to some degree. There's a data set could come from the book. There's some larger ones that get used in bits and pieces throughout the book. You could investigate a larger question more fully on those data sets. There's some data sets from other books in different areas. The internet has a lot of data sets of considerable size, some of them in complexity, that could be used. But when it comes time to that, either for the first one or the second one, we can have a conversation, we can meet in office hours to talk about what you might like to do if you're searching for a particular topic, and I can try and help you find something. If you're doing research projects, either in the past or ongoing, it would have some data, or in another class that has a textbook with some data sets, that one of those might be used. Right? The final part of the class would be some element of participation. Right? And so the idea would be to look at the chapters before class so we can talk about them, so you can ask questions, so we can think about some of the study problems or case studies that are in there. Most of the methods are drawn, illustrated with case studies or actual data analyses. And then I'd like students to be responsible for doing short presentations during the semester, right? So that could be one element of a chapter, right? Or one of the shorter case studies or kind of discussion questions, right? And so if everybody does that twice, and there's 9 of us, 2 times, that's 18. So it's kind of one person a week or 2 people per week doing that. And maybe you could do it in pairs, right, to do it. If it's in pairs, maybe it'd be more like the 10 minutes. But so it's kind of a little experience of presenting that. It's a little more interactive way of doing it. And at the beginning, when we start talking about a couple of those methods, kind of at the start, during this first week on Wednesday, Friday, I'll try to kind of block off some little thing that would be as an example. So say I wanted to do a 5-minute presentation on this case study, right? And well, I would say what it is. All the other students might have read it. They might bring you questions. And the idea then is, you choose it in advance, and so we can talk about it in office hours to get ready, and then it's a way that everybody can get a little practice speaking in front of the group and do a little bit more. Right? So it's not just me presenting stuff that you can figure out and do. At this level, right, and going on, there's a great need and benefit from learning on your own. Right? Reading a book, reading a method, figuring out what is it doing, how could it be used, would it be appropriate. And that's a lot of the nature of statistical consulting. Right? Somebody comes to you with a data set and says, I want to know this. And says, well, is that really possible from your data? Or what are the limitations? And then, they think they need to do a t-test or something. Well, is there correlations in the data? Is it really repeated measures? Or something like that. Are there anything funny with their data? Sometimes they come and they don't even realize they have these massive outliers or typographical errors in their data set, and you kind of discover some of those things for them and help. So you might be investigating, trying to figure out something slightly different in that, and kind of figuring out something and how to present it and talk to somebody else is good. That's most of the standard stuff. We'll follow the college policies about religious holidays, accommodations for disabilities or different learning styles. If any of that applies to you, please let me know, either in office hours or via email or otherwise. If there's a learning difference that calls for, we don't have any exams per se, and things are going to be recorded, but if there's any other issues that pertain to an individual, please let me know, and we'll do our best to make arrangements. The biggest part of academic integrity that applies to this is doing your own work in terms of writing up assignments, writing up a project, doing your own data analyses, and it's really in your best interest to be able to do those things. So, that's a lot of the course mechanics. Any questions? Right, so in terms of introducing this course, right, we'll often use things that we're using statistical models or fitting statistical models to data. So more generally, let's see, how do I, there was, I'm not sure why I'm not quite seeing everything. Okay, let me see if I can put this right. Maybe I closed my little notes. Maybe I closed it by accident. So. But okay, it's in use, but I don't see where it is. Okay. There's always a process of getting used to. Okay, yeah, so. What is meant by, what do you think about when you hear this idea of somebody says this is a model? I'll get this thing closed, okay. So what is a model? Or what would be some examples of some things you might think of when somebody says, is there a model?
An algorithm of some sort. Basically plug some data in and get a result in terms of maybe some data you're looking for.
Uh-huh. So kind of an algorithm. So an algorithm. So you have some data of some sort, some variables and things you measured. It does something to it, and then gives you some output, right? And the algorithm is a set of rules in there that does something like that, right? So in what sense is that modeling something? So this is very, statistical, but let's maybe step back one. This is going to fit within our context. Let's step back. What would be kind of a physical model? When scientists study different things, or right, so when kids are learning about the solar system, right, they might take little balls and put them together and put them in certain spaces in a certain order, maybe color them, and then kind of have them going around, right? That's kind of a physical model of our planetary system, right? Our solar system, right? It looks somewhat real, right? It's not totally dissimilar, right? But it's not giving everything, right? It might have some of the main properties and the general idea, right? But it leaves out some things, right? And so you can learn some things for it or kind of predict it that, eventually if you could elaborate it to make it a little more complex, to make these things move, we get some idea of their relative position over time. Right? So, solar system, right, but it's not, let's see, these are new pins. The other ones had, okay. Eraser. So, very good. Right. So you get the idea of it, but it doesn't have all the details. And you could learn a little something from it. Right? Can anybody think of any other physical models that would be used in some aspect of life?
Maybe like a globe.
Globes, right? Yeah, so globe. Right. It doesn't have all the geographic detail, but it's spinning, and so maybe something like weather patterns, right? Right, so you could have the large the Hadley cells that show the rotation of the atmosphere in different parts, or the jet stream, you might know where that is. It's not all the details, right, but it captures part of the main picture. And if you could have a sort of like an algorithm or code that would say if you start at this place and it goes forward according to a few simple rules, you'll end up someplace, and maybe it's pretty close to what it would be in reality, but there's a lot of other details to it that get left out, right? So it's making it simpler so you can think about it and illustrate it and maybe communicate it, but it's not all the things, right? How about things like, so if you wanted to make an airplane go faster, right, or do, right, you might do something like a wind tunnel, right? Right, so you could have wind going, you stress something out, either expose it to heat or environmental, hail, or you have an engine, that's exposed to things, or wings, and you see how the air goes over it. So that's a part of the thing. So it's a physical model, and you kind of learn from it, and maybe gain some insight into making things better. But there's a lot of other issues going on, right? In some things, right, very much like this, I think about in economics, right, kind of an input, right, or output type model. Like you put so many resources in, and then what comes out of it. So if you have a factory and you're buying supplies and things are coming in kind of at a micro scale, and you have this production process, what's supposed to come out? Well, there's waste and there's imprecision all the way along, so it will come out to pretty much what the algorithm says, but there could be a little bit of deviation, right? At the large scale, at the macro scale, right? So the president and the Federal Reserve argue about how much to cut interest rates to get the economy going. So, they might have an equation. Somehow they're saying if you make that change, it's going to lead to these changes in all these other parts, and in the end, there's going to be some measurable output coming out of that, right? But, I think some of the answers depend on, well, what do you put into the algorithm, and which data do you actually come in, and how do you put it all together? So one model might work a little bit different from others. I wanted to show, okay, I gotta get used to scrolling through that to find my things. On the website, these are just a few models that I came up with. So if you look up climate models, NOAA, climate.gov, NOAA is the National Oceanic Atmospheric Administration, so they keep track of that. They have a nice page, climate models, how we use models. Models help us work through complicated problems and understand complex systems. They allow us to test theories and solutions. Models as simple as toy cars and kitchens, toy kitchens, I guess, to complex representations such as flight simulators, virtual globes. We use models throughout our lives to explore and understand things we work. So their models, they have these grids, latitude, longitude, but then also atmosphere, height or pressure, and a huge number of processes about going back and forth between those little different pixels in there. And so they're based on well-documented physical processes and so on. There's a certain resolution to the model. Is it square meters? Is it square miles, kilometers? Is it at 100 square kilometers, right? So they can be at different levels. They talk about testing models. And so this one was kind of interesting. They test it versus hindcasting, right? So they have this process. They could actually run it backwards from the present. And if they've included enough interactions and factors and data elements that producing most of the change, they run it backwards in time. And if it works fairly well going backwards in time, they reason, well, it should work pretty well going forward in time. Right? To me, I think of right away, well, there would be another way to test some of that, right? Instead of only looking backwards, what else could you do? Presumably that they do it, right? That they look at, we make predictions now, and we can look at, well, what's going to be in 1 year or 5 years? Or if we had data elements from 10 or 20 years ago and made predictions going forward, you can compare that to data and see if it's getting the right average temperature, rainfall for an area, and all that, right? And then it contrasts it to some other models, right? So unlike weather forecasts, climate models are probabilistic, indicating areas with higher chances of warmer or cooler, wetter or drier, and so on, and so on. So I know that was kind of an interesting description of thinking about what a model is and how is it useful. Models come in social science research and all forms of research. This is NIH, MS, National Institutes of Mental, I'm not sure which one. That's just general NIH, National Institutes of Health. And so I worked for a little while with this guy, Fred Lorenz, at the Iowa State University in psychology and statistics, and the nature of their study of looking at things that influence marriage and transfer of knowledge across generations. In Iowa, they collected a number of individuals who were recently married. They got them together and videotaped them in interactions, and then followed them every year for about 30 years. Right? And so they asked them questions about themselves, about their partners, and they did this videotaping of them. And so there's several articles out of this research collaborative. But so the dyadic processes are processes between the husband and wife in these cases, about attributions of what the partner is. Why is the partner doing something? What's their motivation? Are they trying to hurt me? Are they trying to help me? Is it, and so on. The behavior they do and general assessments of marital quality. So this is very complex. There's whole sections about things that they're doing. So they have these samples, 200 married couples. They talk about all the different measures, and each of these measures is not just a yes/no question. It's kind of an inventory of things to assess how things are going. They describe that, but the model they come up with is down there's a picture at the end. And so I'm going to skip through all that. But this is essentially the model they come up with, is that the measurement, the husband's marital quality and the wife's marital quality is what they're looking at. There's behaviors and there's attributions. What are they interpreting behavior as? And they interact with one another, right? And so each one of these things is measured with several different components. And then there's these correlations. about that. And they find that these things are statistically significant, and so how people are thinking about what the partner is doing and what the partner actually is doing have both a direct impact on marital quality, but some of it is through what it's called mediation. The things are, the strength of the relationship is affected by how these things go. But so that in a way that's a model of very complex, social science, psychological science research topic, right? And it can't capture all of reality. I mean, you really can't get into people's minds and get everything that's going on. It's not a 24-hour videotape of their lives and their emotions and things like that. It's surveys done at particular times, but it maybe gives some insight into what affects these processes. So one conclusion is that there is something there, and if you wanted to do some coaching for couples getting ready to get married and so on, there could be some advice saying, what you do and how you think about their motivations is very likely to affect things. Right? So it could have some useful purpose in doing that, besides kind of confirming what you might suspect anyway, but actually to measure it and show it is something. So anyway, that's the kind of an interesting model in another sense. Right? What makes a model a good model?
Just like how
When is a model a good model that we should keep and use somehow? Right. One of these structures, or things that we set up, physical or these conceptual things relating data, one set of data to another set of data or something. When would such a model like this be good? How would you describe a good model? What would be some of the properties it might have? Yeah.
There's a decent R squared.
Decent R squared. So that's a term we will define. So what in general is R squared in a term from linear regression?
The amount of variance in y that's explained by the any x's.
So we'll get the precise definition of this, but it's like the percent. Percent. So it's a percent of variability in an outcome and some people say explained by other variables. And so this percent variability, we'll have measures of that. We'll talk about which are outcome variables and what are some of these other variables. This explained is kind of in quotes, because then sometimes we're going to think about causation and sometimes we're just going to think about association. Right? Sometimes this is phrased as predicted. Right? So how accurately would you predict the other outcomes based on a whole series of variables? Right? And so in some fields, like physical sciences, astronomy, motions of the planets and things, we get R squared predictions basically that are above 0.999, right? It's extremely accurate because we understand the gross large forces and our model can capture those without a whole lot of variables. Something like the marriage one though, R squared there above 0.2, above 20% would be pretty incredible, right? Because the human relationships are so complex and there's so much variability in there that it's hard to narrow it down and see what would really be associated with one beyond a certain level, right? So the percent variability, right? So accuracy, is it capturing the realistic, is it realistic in the sense that it captures most of the main things that people would think about? If it omits key variables or uses them in a very funny way, it might not seem very good. Models can be complex, but if they get really complex, it becomes pretty hard to use some of them. Professor Desjardins was hired this last year into math and statistics, and gave a talk last spring at his interviews about climate models or oceanic models around the Icelandic waters, right? And so some of that model seemed extremely complex on the level of the NOAA models for climate, right? And the computing of it got so complex, it took days with high-powered computers to do that. The collection of data was very intense, and so it's very complex. And the hope is that, as it gets more complex and difficult to use and difficult to communicate, then you get more accuracy, right? And so that's what we're going for. You might do a simple model, and so part of what we'll do in the class is think about how well different models work for prediction, reproducing data, capturing the effect of certain things, right? And some fields, computer science, machine learning, often look at, not just, they'll accept very complex models where it's difficult to see exactly what's going on. So machine learning algorithms and other things, it's kind of like a little black box where you specify a general structure, and out of it still comes a prediction. Right? So you can still look at, do the predictions work well? And a lot of the things that we're going to do, we'll also have kind of an interpretation of coefficients. What does the model mean? What do the different components of it tell us? So we'll look at that as well. Right? Our models are going to be statistical models. Right? So what do we mean by statistical? As opposed to other sorts of models, I suppose. Based on your experience with statistics and data and things, what are some key things that stand out when you think that we're going to make this a statistical model, or there's going to be a statistical element to the study?
We're inputting collected data of some sort.
Yeah, so there's data, right? So yes, that certainly will be part of it. There will be some source of data, right? Yes, we might want to know something about the data collection. Was it a randomized study? Was it an observational study? That will affect how we're going to use the data. There's a data structure. Is it one observation per unit or case? Is it multiple? Do we have a whole series of measurements that represent one concept, or just one-to-one type of thing? Are there missing data? There's many elements of that will be there. Right? In statistics, describing distributions of data, we usually focus on a couple of things. If you had a set of data, what would you describe? What would you want? Say you had a series of numbers, right, from measuring people's heights or their weights or something. What would you want to tell me about those? Yeah.
The mean, standard deviation, and shape of it.
Yeah. So the describing data, mean, standard deviation. and just kind of the shape of the distribution. Is it skewed? Are there outliers and things? Well, the mean things I think about as getting at things like the pattern or trend, right? Or average, right? There's often kind of some pattern or trend that you could be looking like. So if you have a model, maybe it will tell you what the kind of average expected rainfall is. If you just take the average over the last 20 years, you can report that and say, okay, well, here's an average. And that tells you one aspect of the model, kind of where's the main signal, the pattern, the mean value, and things like that, right? And it wouldn't necessarily only be by data, but the models might incorporate some description of a center or a pattern or something like that, right? And the standard deviation, right, there's variability, right? And so statistical, to me, a key aspect is that we capture some measurement of variability. Our data are variable, our inferences have some uncertainty about them, right? And so as opposed to other things that would just show kind of an average change. It's like we are going, like it said at the bottom of that NOAA model page, they're probabilistic. They say what likely will happen, what's the likely ranges, and how likely are the different possibilities. So it's getting at variability. The shape, the shape of the data is important. If you're thinking about it, I'm not sure where to put it exactly in terms of these two things, but it kind of caught up with the variability. Are you every once in a while going to have a flood that surpasses the 500-year flood? Right? And that's kind of like an outlier thing, or is most of the time going to be concentrated? So I think that's pretty close to related to variability. But the statistical models add this extra part, and like the type of models that were used in that study on marriages are called structural equation models. And for each thing that they have, each of those attributes, there's several measures, and there's averages, and there's variability, and there's correlation among them. And so there's all this structure that's in there that's not a one-to-one changing relationship, but has this variability. So a key aspect of that is deciding what is the natural level of variability that's present in a system. Right? They had 280 couples, so that's a sample, that's a limitation. There's variability introduced because you don't have the entire population. But through statistical methods, we can say for certain that there's a very strong probability that there are certain effects and certain things are affecting one another. Right? So statistical models like that structural equation model can be very complex, right? Other ones that are seemingly simple, right, really could have a lot of assumptions behind them and details that you've kind of washed under, that you simplified away, right, that you haven't fully included in the model because you're hoping or arguing, maybe very reasonably, that those things don't have an effect, right? So one of the very simple things that we'll do at the start is compare two groups and then look at their means. Right? So this might happen in a randomized, well, we could have two groups. There's one that's doing exercise, and there's one that's taking a drug, and these individuals maybe are subject to, they're pre-diabetic coming in. That means that they're overweight, but haven't been diagnosed yet with diabetes. The clinical definition for diabetes in terms of blood glucose, and they haven't had that yet, but maybe they're at risk, meaning they've had some higher measurements that put them at risk, and they have other characteristics, higher body mass index, more sedentary, some things with diet, heredity, maybe. Some are going to exercise, and some are taking a drug. And we might want to see which is more effective. And so maybe we look at average weight loss. So we might have an X bar for the exercise group and an X bar average for the drug group. And we could look at just the difference of these things. Right? And that would seem to be a pretty simple setup, right, for this. And we might set up a hypothesis. Is the average of this group equal to the average of this group, or is one bigger than the other? But in doing this, in a way of setting up a model, right, the model that we've been thinking of is there really essentially kind of one distribution where here's the average and here's this Greek letter mu for more the population average. These are more the sample values. And we'll redefine notation as we come back to this in chapter 1. But the model says there's one group, and maybe this is the distribution of the data values, the xi's. Another model would say that no, there's these two groups, but there's one average over here and there's one average over here. So that they're different. Right? In a way, that's a very simple model, saying if you have one population with one equal mean or something like this. And of course, there's variability because the individuals are not all at the same level of weight loss. Not everybody loses 5 pounds or 7 pounds or whatever. So there's variability. And the model is, are these two? That seems fine. Right? What are some kind of hidden assumptions, or how could this become, in reality, be more complex? Yes.
Well, you need to make sure that people are actually doing the exercise, and how much are they exercising? Are they taking the drug?
Yeah. So in practice, these categories, are they exercising or drug? If that's self-report, are they actually doing it? Right? And what is the standard? What does the exercise mean? So there could be a lot of measurement issues, verification issues that they're doing that. Yeah. Anything else? I kind of avoided saying this was a randomized study, right? If these are self-selected to these groups, well, maybe the ones that are exercising are younger and healthier, right? And the ones that are taking the drugs are older or something like that. Maybe some are living in Vermont where there's a lot of chances to walk around, and some are living in cities where they don't feel as comfortable. You know, whatever. There could be many different differences. But if it's a randomized controlled trial and people have flipped a coin, and then the people have been given information, you should exercise more and here's how to do it. Or here we recommend that you take this drug, right? If it's a randomized clinical trial, you might feel differently about it than it's just observing two groups, right? Any other things that's kind of hidden under this, right? Some things, we often assume that these two groups are independent of one another, right? That they don't know what the other people are doing, or they're not collaborating in some way. In early drug trials related to HIV/AIDS, there was a real issue that people would collaborate and compare experiences and trade drugs or merge drugs, and they're desperate, and so it was a lot of the study designs were compromised because these individuals are no longer independent. In education, there's often a very difficulty of testing because people learn in groups, and the impact of different advertising things. Back in the 80s, the tobacco companies were found guilty of promoting addiction and lying about it, and had to pay something like $200 billion to the states. I mean, it was enormous, right? And they evaluated part of the money went to health treatment, but part of it went to education, right? And of course, if you're going to spend that much money, you're going to evaluate what you're doing. So, what's the impact of an advertising campaign? Well, it's hard to do a randomized experiment within one city because some people, it's hard to control who sees it, right? And things like that. So, people are not necessarily independent. You could also have maybe couples right? If you have a couple living together and they're both exercising, maybe that's different than just an individual doing it. When we would do inference, statistical inference to measure the level of variability, that would impact how precise we would think that these things would be if you have people clustered together versus completely independent, right? Sample sizes play a role. The measurement, are they really measuring the same concept? This is, as it's set up, this would not be a blinded study. People would know that they're exercising. People would know that they're taking drugs. If people had to weigh them and evaluate them, it'd be hard for them not to talk about what they're doing. If this was certainly evaluating somebody's psychology, are they happy with it? How do they feel, right? And then somebody knows that, oh, you're exercising or you're taking that drug. The people evaluating that might score them a little bit differently. They might try to be perfectly objective, but if they know that somebody comes and says, yeah, I've done a lot of exercise, right, then, oh, that's a positive thing. Be kind of swayed to giving positive evaluations of other things. And so the whole measurement process could affect this. So even things that seem like simple models, one average versus two averages, have some underlying assumptions that you want to know about. From a data perspective, we might look at the distribution of data. Does it look, even this kind of bell-shaped curve, if there seem like there's subgroups in there or some people that are really outlying relative to the others, we might want to know that shape. That might affect how we want to analyze the data and effectively how we want to, do we need to kind of elaborate the underlying model, make it more complex, because our data and our reality is really more complex. At some point, a simple model will work for us and do good predictions and be useful, but if the underlying situation which we discover is actually more complex because we know more details about the study design or look at the data, then we can make our models more complex. Right? So in this, we'll look at a lot of different ways to analyze data, but in part of it is kind of checking these underlying things and thinking about, well, how can it be more complicated? Right? And some of the fulfilling consulting activities that I've had over time is people bring data and they think it's pretty simple, but there's just a little bit more complexity. Like in educational testing, there's an order effect. If you're going to test people over and over again, there's a, and you can incorporate that extra element into the analysis to make it more precise. And they didn't realize that up front, right? So, right. So we're going to be looking at a whole bunch of models and corresponding to data, looking at trying to answer questions about that, do predictions, make conclusions in applied contexts, and then trying to assess, is the model appropriate? Right? And sometimes we'll go a little bit beyond the models, introduce a few alternative ways of looking at how would you quantify variability, uncertainty about these things. Right? And so the request for Wednesday would be to look through chapter 1. Right? We'll start out looking at some of the inference for just one means and what's a standard error and some of those things. I put a couple other model examples in here. One I'll show. Models get used in a number of things. So my brother's a pediatric dentist, and every once in a while he calls me, help, I have some data. And so he's the lead author in this. And one thing that they did with dental students at NYU and a couple other places is go down to Jamaica to go for a week or two. And they did this for about a 5-year period to go to a collection of schools down there, just provide free dental care in the schools for the kids. And it's an area that's fairly rural and impoverished, and so many of the students, the kids, they don't necessarily come to school right at kindergarten, they don't necessarily have dental care up to that point. Some do, but some don't. And then the question that they were interested in is if you place sealants on molars, like is often done in the US and other countries, what would be the outcome for these children? Because when they're about 5, 6 in school and their molars are beginning to erupt, and you put that on, it should protect them, and then they should have less decay at 6, 7, 8, things like that. And so the data, here's some of the kids with their teeth. This is New York State Dental Journal. And so, you could measure that some of the kids had no decay at the start, some had decay later on. What was the impact of the second? And in this case, it was what is the impact of repeated visits? Well, these repeated visits, and it was estimating a probability. So we actually fit a logistic regression model, which is predictive probability, which we'll cover later towards the end of the semester. There were multiple visits on each child, so it had this random effect of kind of the effect of that particular child was there. And so we wanted to study those, and did any of these things impact that? And so to do this, here's this big table. We fit a bunch of different models. Right? So we didn't have a lot of data. There weren't a whole lot of kids that had that many repeated visits, a couple hundred. And it was not really, you couldn't find out a lot about their home life and some other things. So there's a substantial statement of limitations of the study. But here's one model where we're predicting to predict decay based on did they have a previous visit, yes or no. This one did how many visits do they have. Here's a variable, any previous visit versus the number of visits, where you have a couple different ways of looking at the same variable. Right? Did they ever seal their molars? How many times did they have them sealed? Because the seals can be reapplied as they come back. Right? And all these things were statistically significant. AIC, or percent correctly classified, is kind of like the R-squared measure. And it did a pretty good job of classifying. But then you might put age into there, because some of the children started when they were 5, some started when they were 7. And a couple more years, Jamaica produces a lot of sugar cane. And if you're not brushing your teeth and just eating sugar cane, your baby teeth won't last very long. But there's an impact of age, and sometimes that was significant. The other variables were still. There's this other model selection called AIC, this information criterion. And so if you had to pick one of these models as the one that seems to do the best job of fitting the data without overly fitting it, right? Not throwing you could throw the whole kitchen sink of variables in there and get a higher prediction, but you might not be too happy about that for use in the future, just because, I don't know. So you can get little aspects of your particular small sample, and if your model fits those, that might not be present in the future, right? It might not be a general pattern. It just might be a little quirk or something about that, right? And then there's some ones with some more variables in there. And the point of using models here is not to find the perfect model that reproduces everything, right? But the conclusion was it certainly seemed all these different ways of measuring the interaction seemed positive. It seemed to reduce the amount of decay at subsequent visits. And across these different models, none of which is perfect, it seemed to make a pretty big difference. Right? So in a way, this particular model, there's a lot of assumptions underlying those things. We didn't really know if the children had siblings there. Didn't really have access to the family records. So there's limitations, but it was an attempt to use models to try and learn something and show a general pattern. There's other dental models that actually model the spread of decay around the mouth that are extremely detailed. Right, so there is a very sophisticated modeling that does the spatial temporal things, but these data weren't really appropriate for that. So I'll collect those little survey sheets, questionnaires, to learn a little bit more about you. I've had some of you in class before, and met you at other times, so it's great to be back with familiar faces. And look forward to this message.
Yeah, I'm gonna check. I think that's really good.
Very good.
I just wanted to quickly check in about the paperwork for that.
I think you're listed on my, you're on the other 252?
Yeah, I'm in 252. I'm not in this Canvas
Right.
like course either.
Okay. But, yeah, I think we should get you access for that. Ad drop is due the 3rd, so next Tuesday, and I don't know if you have to add this as an audit, but
Okay.
it'd be desirable for you to be on Canvas.
Yeah, I was,
To get things.
I tried to register for it, but my vision like gave me an error because I like already have credit for it.
Okay.
But yeah, I just wasn't sure if like there was a certain thing I had to do to like officially audit it or anything.
What's your, do you know your student ID
Yeah,
number?
it's 57919.
Get my receipt to return this book and then you get an ad drop.
How do you spell your last name? W-I-L?
WILCZPWSKI.
I'll see what I can find out, and we'll
Okay.
we need to fill a form, or maybe I can just write the registrar and see if they can add you to Canvas, or and probably monitors like Canvas, maybe we can just add you
Okay.
to that. Is this something that would be desirable to have on your, I don't know if they can put it on your, if they list audited courses on the transcript. I don't know if they do that.
I don't know either. But I do have good credit for this on my transcript already. But yeah, it would also be good to like show that I audited it. But also, so am I doing the homeworks and projects as well? Or?
Yeah, so as auditing, since it's not for a grade, you don't necessarily have to do them. It's a small enough class that if you want to do anything and have it checked, or, you know, I encourage you to look at the data set, look at the assignments, and whether you write it up formally kind of is up to you. If you have questions about it, you can come ask
Okay.
questions about things, but yeah, not necessarily. If you are doing a senior, or doing, if you want to make a presentation at the end, kind of as part, and be part of the group, in that sense, you can make a presentation, whether you write up an independent project or not. If you have other past experience or something you're working on, or you know, if you're motivated to describe, try some of the methods on a data set you want, and then want to talk about that, you'd be welcome to do that, but it wouldn't be required either. So.
Okay.
Okay.
Sounds good.
Yeah,
Thank you. I'll see you later today for.
that's right.
You too.
252.
All right. Have a good one.